Welcome back to the YouTube channel. Today we are going to be exploring the Feynman technique of integration. Now this is the biggest cheat code in the entirety of integration. It is a very beautiful technique created by Richard Feynman. Well, it wasn't really created by him. It's quite a controversy on whether it should be called the Feynman technique or the Leibniz technique. And that is because Feynman uses the Leibniz integral rule together with functions to add a parameter inside the integral. And then by differentiating said integral, it simplifies into a piece of cake anybody can do. So, I believe the best way to showcase or teach the Feynman technique is by doing an example and demonstrating it on the board. So here we have the integral from 0 to 1 of x minus 1 over ln x dx. So, first things first, let's create a function of this integral and add our parameter. Let's let our function be I, let's use I, and let the parameter be t, and we want to place our parameter in the exponent position of this x here. Therefore, I of t is equal to the integral from 0 to 1 of x to the power of t minus 1 over ln x dx. Now, notice if we take t as 1, this integral turns into our main question here. Therefore, we can actually equate our main question into I of 1. And this is important later on, I'll show you why. So, when we use the Feynman technique, after we create a function, we want to differentiate both sides. So I dash of t is equal to d over dt of our function here. Now, using the Leibniz integral rule, we can actually put this differential operator inside our integral by turning it into a partial differential with respect to the variable we want to differentiate. Now, I have mentioned the Leibniz integral rule before on my channel, and that is under the video talking about the differential of the factorial function if you want to check it out. But I will also link the Wikipedia page of the Leibniz integral rule if you want to check that out instead. So, our integral changed into the integral of 0 to 1 of the partial differentiation with respect to t of x to the power of t minus 1 over ln x. Now this is a very simple exponent differential because we treat x as a constant here because we're taking the partial differential with respect to t. So we treat x as a constant, and this is just a simple exponential differential, which is very easy. Everybody knows how to do that, so I'm not going to really go into how to do that. So let me rewrite our integral here as the integral of x to the power of t times ln x over ln x dx. Now notice these two ln x's can just cancel out, correct? So let me write it down here. I dash of t is just equal to the integral from 0 to 1 of x to the power of t dx. Now this is a very simple integral. It is anything but hard. Okay, so that if we integrate this, we get that I dash of t is just equal to 1 over t plus 1. Now there is a plus c here. However, we don't need to write it now because we're going to actually integrate both sides. Now the reason we want to integrate both sides is because we want to get rid of this dash here. And if we integrate this, what we get is I of t is equal to ln of the absolute value of t plus 1 plus c. Now, we have to find out what this c is here, and we can do that very easily. But let me go to the small board here because I want to remind you of something. So, recall that I of t was equal to the integral from 0 to 1 of x to the power of t minus 1 over ln x dx. So, if these two functions here are both equal to I of t, why don't we equate both of them to each other and take t as 0 to find what c is? So if we take t as 0 and equate both functions together, we're going to get that 0 is equal to 0 plus c. That's what we're going to get. So c is just equal to 0. So let me erase this, and let me also erase our c because it's just 0. Now remember, at the start of the video, or at the start of the problem, we said that our integral turns into our main question when we plug in I of 1. So when we plug in I of 1 here, all we're going to get is ln 2. So this entire integral is just equal to ln 2. And just like that, that integral is done very simply and beautifully and elegantly using the Feynman technique of integration. Now, let's do another problem here, because this one was done in a very short amount of time. So let's do another problem, one that's a little bit more complicated. So I'll erase the board and I'll cut into the second problem. So here we have the integral from 0 to infinity of sine x over x dx. Now the problem is with this integral is this x in the denominator here. We want to get rid of this x. So if one were to use the Feynman technique, one might be inclined to put t next to x here. However, that's not going to work, and I'll show you why right now. So let's say I of t is equal to the integral from 0 to infinity of sine tx over x dx. So if you differentiate both sides, you're going to get that I dash of t is equal to the integral from 0 to infinity of cosine tx dx. Now the problem is the function inside the integral, it does not quite converge, it diverges. So if you evaluate it, you're going to see that it does not converge, it diverges. Now that's a problem. So let's start it over. The correct way of actually evaluating this integral using the Feynman technique is to actually multiply the entire function inside the integral by e to the power of negative tx. So let me show you this. So I of t is equal to the integral from 0 to infinity of sine x over x multiplied by e to the power of negative tx dx. Now notice that if we take t as 0, this integral turns into our main question. So we can equate this to I of 0. Now remember, I already said that this will actually be important later on, and you probably know why. So if we differentiate both sides, we get that I dash t is equal to the integral from 0 to infinity of negative sine x multiplied by e to the power of negative tx dx. Now we can actually integrate this using integration by parts. So if we integrate this using integration by parts, we're going to get this. Let me show you. We're going to get that I dash of t is equal to negative 1 over 1 plus t squared. There is a plus c here, but we're not going to need it because if you remember, we're going to integrate both sides. Now this is going to give us that I of t is equal to negative arctan of t plus c. Now we have to find out what c is. And remember, I of t is also equal to this integral. So if we equate both of them, and this time we're going to let t approach infinity, we're going to get that 0 is equal to negative pi over 2 plus c. And this implies that c is equal to pi over 2. So let me substitute that into our equation. Pi over 2. Now remember, when t equals 0, this is the same as our main question here. And if we plug in t equals 0, our integral is equal to pi over 2. And just like that, we have solved this very difficult question, or most people think it's a very difficult question, very easily in like 4, maybe 5 steps using the Feynman technique. This really is the biggest cheat code in the entirety of integration. Thank you for watching the video. I hope you learned something. Have a good day. Bye bye.